Okay, so the next video we're doing is all about standard deviation, linear interpolation, medians, means, and histograms. Let's have a look at this question here. We've got a midwife who records the weights in kilograms of a sample of 50 babies born at a hospital. Her results are given in the table below here. And histogram has been drawn to represent this data. The bar representing the weight 2 to 3 has a width of 1 centimetre and a height of 4 centimetres. If we do a quick diagram of that there, that's from 2 to 3. And if we have a look at the frequency, sorry, it's got a height of 4 centimetres. Now the frequency for the 2 to 3 bar is 8. Now when you do histograms, the frequency has got to be the area of the bar. So if this has got a width of 1, therefore the height must be, so the frequency density must be 8 to make, because 1 times 8 is 8, so therefore the area of this bar must be 8. So the y-axis there must be 8 for this bar. Now we've got to work out the width and height of the bar representing 3 to 3.5. So 3 to 3.5 is only a half there. So 2 to 3 has a width of 1 centimetre. So that's a width of 1, and that's 1 centimetre. So width of a half is a half centimetre. So we say that the width is 0.5 centimetres. Now if we have a look at the frequency for this one, which remember the frequency is the area of a bar with a histogram. The frequency, so the area is 17. So therefore, if the width of the bar is 0.5, the height must be 34. So therefore the frequency density must go up to 34. Now if we have a look back at this question here, the bar representing 2 to 3, the frequency density was 8, and that's got a height of 4 centimetres. So frequency density of 8 is 4 centimetres. So therefore the frequency density of 34, to go from the frequency density to the height here, we divide by 2, so that's going to be 17 centimetres. And that's how you work that one out. But the key thing here is for histograms that the frequency is the area of the bar. Now the next set of questions talks about linear interpolation. Now linear interpolation, there's a couple of ways of doing it. Now I think the way I'm going to do it is the easiest to understand. That's only because I understand it. If you prefer doing it a different way, that's absolutely fine. But if we've got to find the median, we've got 25 babies here. Now because it's interpolation and we haven't got the raw data, we're going to look, we don't add 1 and divide by 2. Because it's in a table and it's linear interpolation, we just divide by 2. So 50 divided by 2 is 25. So what we're doing basically is we're looking for the 25th baby. Now the first baby is here. The next 8 babies, that's 9 up until this point, lie in this one here. So the 10th baby, all the way up to and the next 17, so that's going to be up to the 27th baby, so 26th baby, is going to lie in this category here. So the way we use linear interpolation to find the median is once we've identified the category, we start with the lower bound, which in this case is 3. Now you've got to be careful with this one. Often it's going to be halfway between this value and this value, but because they're the same, the lower bound must be 3. So it's going to be 3 plus. Now we're looking for the 25th baby. And the first 9 babies are here, so we want to find the 16th baby after that. So we are looking for the 16th baby, but there are 17 babies in here, so it's the 16th out of the 17th baby in this category here that's going to be the 25th one. So it's the 16th out of the 17th, or 16th out of the 17 babies, and then we multiply this here by the class width. Now the class width is between 3 and 5. Now again, you have to be careful when you're doing different questions, because sometimes that could be 2.5 up to whatever the upper boundary for that one is. But here, the boundary starts at 3 and it ends at 3.5. So therefore, the class width is simply 0.5. And then you type that into your calculator. And that gives us 59 over 17, which equals 3.47. Of course, doing it to 3 significant figures, because that's what statistics papers look for. As we said in most of the other videos, it's 3 significant figures. Okay, so now, show that the estimate of the mean weight of these babies is 3.43 kilograms. Now, the mean, what we do for the mean is we multiply the frequency by the midpoint. Here they've given us what the midpoints are, so we multiply those together and we get these values here. So it's going to be 8 times 2.5 is 20. 17 times 3.25 is 55.25. 17 times 3.75 is 63.75. And then 7 times 4.5 is 31.5. And then what we do once we've done that is we add them all together and we divide by the total frequency. So the total frequency is 50. We can either add them up or it tells what the total frequency is. If we add up this column is 171.5. So then we do 171.5 divided by 50, which equals 3.43, and then we got our marks there. And now we've got to find an estimate for the standard deviation. Now, the standard deviation, if we make ourselves some room here, the standard deviation is the sum of x squared divided by n minus the mean, which is the sum of x over n squared. Then we square root all of that. Now, we've been told, right, when we've got a table, what we do is let's explain this a little bit better. We take the midpoint, which we know is 1, we then square that, and then we times it by 1. So it's going to be 1 squared times by 1, 2.5 squared times by 8, 3.25 squared times by 17, and that's going to give us this value here. So once we've got that, we then divide by n, which in this case is 50. Now this question has been rather kind to us, and it's told us what the sum of x squared is times by the frequency. So they've already given us that number, which is 611.375. And what we do is we divide that by the total number, which is 50. Then we take away the sum of x over n squared. Now, this sum of x over n, that's how you find the mean. So that's going to be 3.43 squared. Once we've done that, we square root it. And that gives us 0.680. So 0.680. So actually it's worth saying this was 3.47, so we're going to need to use all this in a second. Right, so that's the estimate for the standard deviation. Now the next question starts talking about, well, we've got this n here, which means normal distribution. And I am going to go through that because it's this question anyway. But we're also going to do a separate video on normal distribution afterwards. So Shyam decides to model the weights of babies born at the hospital by the random variable w, where w is normally distributed with mean 3.45 and 0.65 squared as the standard deviation. Find w is less than 3. So with normal distribution questions, what we do is, or what I do, okay, let's do a little bit small as we can fit a couple of diagrams in. So we've got our W curve here, and I'd always sketch the curve they're talking about. So they're talking about a W curve, and the mean is 3.43, and we've got to work out the probability that it's less, that the weight is less than 3. Now, if the mean, or the median, sorry, is 3.43, then that's going to be halfway. So this area here is going to be significantly less than halfway. So if we've got a probability of 0.6, we know we've made a mistake, and that's a key thing. For this sort of question, is we have a look and see whether or not our answers make sense. Once we've got our W curve, we don't know any information about W curve other than what we've got written down there. So we try and do an identical curve, but call this one the Z curve. And I want to find out what this corresponding value here is. Now, the way you work that out is to work out your Z value, you do whatever your value is, take away the mean, divided by the standard deviation. So in this case, it would be our W value, take away the mean, divided by the standard deviation. So our Z value is going to be 3, take away our mean, which is 3.43, and divide by the standard deviation, which is 0.65. And if we do that, we get 3 minus 3.43 divided by 0.65, and we get minus 0.66153. Now, usually we do it 3 significant figures, but we're going to make an exception here because we can't find this 0.661 in our tables. So what we're now looking for is if I draw it over here to the left, we've got our Z curve here, and I want to know minus 0.66, what that area is there. Okay, now this is a bit where people find it tricky. Now if we have a look at the tables, the Z tables in our formula booklet, we've got this here. Now notice that we have got to try and find the value in our Z curve of minus 0.66. But we don't have any negative numbers. What we do have is 0.66 here, which is 0.7454. But that's for 0.66. So if we then use symmetry, so 0.66, that 0.7454 is this area here, the probability that's less than 0.66. But this area here that we're looking for is going to be the same as this here because of the symmetry. Minus 0.66 is the same as 0.66. So this area here is going to be the same as this area here. So the way we work out this area here is we do 1 take away this 0.7454. And if we do that, we get 0.2546. Now, we have got to now make reference to B, C1 and D to comment on Shyam's decision. And his decision was to use the normal distribution. So let's have a look at everything that he's done so far. So he's used the normal distribution. Now, with the normal distribution, the mean and the median have to pretty much be the same. Let's have a look. So the mean, which was 3.43, and the median, which was 3.47. That's completely up to you now. You can say there's a difference of 0.04, so because they're not the same, we can't use the normal distribution. Personally, I would say that are very similar. Therefore, normal distribution is appropriate. Now, what we've done there is we used B, which is the median, and C part 1, which is the mean. So we've done that bit and that bit. So now we've got to comment on D, because it says you've got to reference all 3 parts. So if we comment on D, what we've done is we've worked out the probability that the weight is less than 3 is 0.2546. So how do we reference that? Well, what is the probability that the babies are less than 3? There are 50 babies in total, and if we have a look, these were less than 3, these were less than 3, but these were all 3 or above. So there were 9 out of 50 babies that are actually less than 3. So 9 out of 50 equals 0.18. So what I would say is after this, I would say, however, the probability that the weight is less than 3 is 0.2546 using the normal, but in reality was 0.18. Therefore, normal not appropriate. Then I have an overall answer. Overall not appropriate due to probability not matching. And I'd be confident that would get me all 3 marks. Okay, so state, without carrying any further calculations, let's get rid of all the calculations that we've got so far. Okay, so without doing any further calculations, state, given a reason, what effect the addition of this newborn baby to the sample would have on the estimate for the mean and standard deviation. That tells us the newborn baby weighs 3.43. So, if the mean was 3.43 and the new baby is 3.43, the mean would remain the same. So given the reason, as it is already the same as the mean. Now part 2, the standard deviation. Now this is all about understanding what the standard deviation is. Now the standard deviation measures on average how far away from the mean each piece of data is. So the standard deviation would decrease as the new data is already the mean. Therefore, on average, the data would vary from the mean less. And that's what you do. That's how you answer that question. Now, this was a 2015 question on this. Each of 60 students were asked to draw a 20-degree angle without using a protractor. The size of each angle was measured. The results are summarized in the box plot below. Find the range for these data. Now, this was done relatively poorly. The range isn't from this one to this one. It's from the smallest to the biggest piece of data. Now, the smallest piece of data for this was 9. But the biggest piece of data was this one out here, which is 48. So it's 48 take away 9, which equals 39. So just be careful with that. The interquartile range is from this quartile here to this quartile here, which is 25 to 12. So that's going to be 13. Okay, so the students were then asked to draw a 70-degree angle. The results are summarized in the table below. We've got to use linear interpolation to estimate the size of the median angle drawn. So again, linear interpolation, we've got a table, so there's 60 pieces of data here. So we're going to find the median, which is the 30th. So the 30th piece of data, the first 6 are here, the next 15 are here, so that's 21. So up to the 34th piece of data is here. So here is where the median lies. So we start off using the lower bound, which is 65. Now if we're looking for the 30th piece of data, the first 21 are here, so we're looking for the 9th piece of data into this. So it's going to be 9 out of 13 times by the class width, which is between 65 and 70, so that's 5. Now this gives us 68.5 degrees. Show that the lower quartile is 63. So if you're looking for the lower quartile, just like the median you divide by 2, the lower quartile is a quarter of the way, so you divide by 4. So 60 divided by 4 is going to be 15, so we've got to find the 15th piece of data. So the first 6 are here, and if we're looking for the 15th piece of data, that's going to be 9 more. So we're looking for the 9th, which will be in this category here. So the lower bound is 60. It's going to be 60. If you're looking for the 15th piece of data, you're going to be looking for the 9th out of those 15. You times by the class width, which in this case, again, is 5. And if you do that, you get 63. So that is how you show that the lower quartile is 63. For these data, the upper quartile is 75, the minimum is 55, and the maximum is 85. An outlier is this thing here. So there are no outliers for this data. So if the outlier is 1.5 times the interquartile range, if the lower quartile is 63 and the upper quartile is 75, then the interquartile range is 75 take away 63, which equals 12. Now 1.5 times interquartile range, 1.5 times by 12 equals 18. So an outlier is if it's this much, so 1.5 times interquartile range, so 18, below the lower quartile or above the upper quartile. So if we have a look at the lower quartile, which was 63, and we take away 18, 63 take away 18 is 45, and if we have a look at the upper quartile, 75 plus 18 equals 93, so 45. Now the minimum is 55 and the maximum is 84, so the minimum doesn't go below this and the maximum doesn't go above this. So as that, and then because it says show that, it means that you're going to need to further explain that. So no data, or we say that 55 is above 45 and 84 is below 93. And we're going to draw box plots using this grid here. So the minimum data is 55, so I'm going to draw a line at 55. The maximum is 84, so 1, 2, 3, 4 there. And the upper quartile was 75, so let's do that one. Nice and easy marks, these ones. The minimum, the median was, what do we say the median was? 68.5. So kind of hard to do it on here, but 68.5. Make sure it's in between the 68th and the 69th piece of data there. And the lower boundary was 63, so lower quartile, sorry. That there. And then you draw your box plot. State which angle the students were more accurate at drawing, give reasons for your answer. So if we have a look at this, is worth 3 marks. So when we had a 20-degree angle, the median here was 16. When we had to find a 70-degree angle, it was 68.5. So I'd say that the 70-degree angle, write this down, 70-degree angle was more accurate as median is only 1.5 degrees out, whereas 20-degree angle median was 4 degrees out. It's worth 3 marks, so you really have to say something else. And if we have a look at the interquartile range, the interquartile range for 20 degrees was in between 12 and 25, that's 13. but only it was only 12 for 70 degrees, therefore data less spread out, or less varied. So again, that's how you do that question. Again, same question. And this one was the 2014 paper on the same topic. So if we have a look at this one, we've got the 30 to 60 group. So again, let's do a little diagram. So 30 to 60, that has got a frequency of 10, which means that the area of that bar has got to be 10. So if the width is 30, and then the area's got to be 10, therefore that's going to be a third. So now we've got to work out what it is from 70 to 80. So if this has got a width of 1.5 centimeters, 30 has a gap of 30 has a width of 1.5 centimeters. So a gap of 10 is going to be 0.5 centimeters. That's going to be for the width, 0.5 centimeters. If you have a look at the 70 to 80 group, that has got a frequency of 25. So 10 times by something makes 25, so therefore that's going to need to have a frequency density of 2.5. So we know that 1/3 for this one had a height of 1 centimeters. So we need to know what a height of 2.5 or what a frequency density of 2.5 is going to give us. So how many times does a third go into 2.5? So if we do 2.5 divided by 1/3, we get 7.5. So if we multiply a third by 7.5, we're going to get 2.5. So multiply this 1 centimeter by 7.5, we're going to get 7.5 centimeters. Not straightforward, that one. But let's have a look at part B, because part B I think will be straightforward if you've had to look at the other two questions. So we've got linear interpolation again, and we're going to find the median. So the linear interpolation, we've got 85 pieces of data here, so if we halve that, it's going to be 42.5. So we've got to find where the 42.5 piece of data is. So if we add up, so if that's 2, that's 12, that's 29, and then the next 25, which take us up to 54. So therefore, the 42.5 piece of data is going to lie in this category here. So the median is going to be 70 plus. Now, if we're looking for the 42.5 and the first 29 are here, we're looking for the 13.5 in this category here. So it's going to be 13.5 out of the 25 that's in that category times by the class width. Now the class width goes from 70 to 80. Again, double check. This one starts at 70, this one ends at 70. If the last one ended at 69, then the lower boundary there would be 69.5. That's not the case, but sometimes it is, so just be on the lookout for that. So the class width, like I said, was 10. And if you do that, 13.5 divided by 25 times by 10 plus 70 should get you 75.4. And that's how to work that one out there. So now what we've got here is x denotes the midpoint of each of the groups, so we've got to work out an estimate for the mean. So what we do is we do the midpoint times by this one, the midpoint times by this, midpoint times by that. And what they've done here is they've given us what that equals. So all of those equals 6,460. So it's going to be 6,460 divided by the total number, which in this case is 85. So 6,460 divided by 85 gives us 76. Now the standard deviation, again, this has gone from a couple of videos now, so it's the sum of x squared divided by n. Now remember, the sum of x squared isn't the sum of x squared. It's sum of x squared, which is the midpoint, which is 15 squared times by 2. 45 squared times by 10, but again, they've told us that. And that's take away the mean squared. So that's going to give us, if we put that into our calculator, 529400 divided by n, which in this case is 85. Take away the mean squared, so take away 76 squared. And all that should give us, that gives us to three significant figures, 21.3. Now, one measure of skewness is given by this here. So we've got to evaluate this coefficient, that's going to be at least 1 mark, and then comment on the skewness of the data. So we're going to need to do 3 lots of the mean, take away the median. So if we do that, it's going to be 3 times by 76. And the median we had was 75.4. Divided by the standard deviation, which is 21.3. So 3 times by 0.6 divided by 21.3, and we get 0.0845. Again, 3 significant figures. So that's evaluating the coefficient, and then we've got to comment on the skewness of the data. So we can see this is very slightly positive, so we could say very slight positive skew, or because it's very close to 0, we could say no skew or normally distributed because this is very small. Either one of those will get us all 3 marks. And that's how to do the linear interpolation and this sort of question.